Okay, so today is a very important day for you. You're learning probably one of the most important concepts in mathematics, Taylor and Maclaurin series. Now, let me give you a little perspective of where we are. Let me go to the whiteboard here. Right now in section 8.6, you learned that you could take a function 1 over 1 minus x and write that as a power series. Okay, and the interval of convergence was x is between -1 and 1. And from there, we were able to say, well, what if we didn't have an x? What if we didn't have an x here? What if we had something different? What if we had like 1 over 1 minus x squared, for instance? Could we get a power series for that? Well, we could if we treated the x squared like an apple. Okay, because if we piggyback off of the formula here, then 1 over 1 minus the apple is going to equal the summation where n equals 0 to infinity of the apple to the nth power. And of course, the interval of convergence is that the apple is between -1 and 1. So given then, especially the second formula, which is more general, we learn that we could take functions like 1 over 1 minus x squared, okay, or 1 over 1 plus x squared, okay, or we could take like x cubed over 3 plus 2x squared, okay. All of those type of functions, we can manipulate them and get those functions, or utilize a part of those functions to get them in this form here. Okay, so in other words, using this apple formula here, we're able to take certain rational functions and rewrite them as power series, okay, by manipulating the function, maybe sometimes differentiating the function, but ultimately it comes down to being able to use this apple formula here. But this is somewhat restrictive. What if our function were f of x equals like the sine of x? Okay, one moment. Okay, so what if our function were like something like f of x equals the sine of x? Okay, or f of x was equal to e to the x power. Okay, well, those are very common functions that you've studied in past classes. Okay, and it would be desirable to be able to find power series for those type of functions as well. Okay. Another one would be, what about f of x equals the arctangent of x? That's another one. Well, the arctangent of x, actually, you could use section 8.6 to help you with that, right? That's shown in the book. But certainly these two functions here, the sine of x and e to the x, those functions, section 8.6 is not going to be helpful for us to get the power series for those functions. So now those functions, the sine of x and e to the x, you notice they're differentiable and they're continuous. So what if we could find a general way to find a power series for any continuous differentiable function? What if there were a general way to find a power series for that type of function? Well, that's what section 8.7 is about, okay? And section 8.7 deals with what are called Taylor and Maclaurin series. Okay, so I want to just show you, there's a formula there's a formula, and for these series, and I want to show you how they get the formula. Okay, so let me just kind of remove a little bit of the highlighting here. Okay, so again, here in the preceding section, we were able to find power series representation we were able to find in the previous section power series representations for a certain restricted class of functions. Okay, and again, all the functions that we saw in section 8.6 had some relationship to a rational function. Okay, and here we investigate more general problems. Which functions have power series representations? How can we find such representations? Okay, now this approach that we're doing is named after the mathematician Brooke Taylor, okay, who lived from 1685 to 1731. Okay, so you know, the idea of taking a function and being able to represent it as a power series is an idea that has been in mathematics for a long time, and there are very good reasons why mathematicians wanted to be able to do this. And actually, you already saw from section 8.6 that if you can represent a function as a power series, it allows you to, for instance, compute, well, to approximate definite integrals, for example. Okay, and that's important, right? That's important because not every integral has an antiderivative. So here's what we're going to do. Here's what we're going to do. Let's find a way to find a power series representation for a more general approach that can be applied to many continuous and differentiable functions. So first of all, we say, okay, well, we know, and I guess I'm going to have it not highlight. I'll just highlight this here. One moment. Yeah, let me highlight that in yellow. So suppose we could represent a function by a power series in this form. So the function f of x equals c sub 0 plus c sub 1, okay, that coefficient, and times x minus a, plus c sub 2, that coefficient, times x minus a squared, plus c sub 3 times, you know, x minus a cubed, and so forth. In other words, the power series has that appearance. Okay. Well, this power series I mean, we're given what a is. Okay, we're going to be given what a is in our problems, but we need to determine what those coefficients are. You know, what are c sub 0, c sub 1, c sub 2, c sub 3, and so forth. So what we need to do is we need to try to determine those coefficients. Okay, and first what we're going to do is the following here. Let's put in x equals a in the highlighted power series for f of x above. Okay, so we can let x equals a, and if we substitute in x equals a in the power series above, they say in that case that the first coefficient is equal to f of a. It's really not a coefficient, but they call it that. Now let me show you why, you know, why that's true. So let me just go here to the whiteboard. Okay, let me go to the whiteboard and write down the general form of the power series. centered about x equals a. And by the way, when they say that the absolute value of x minus a is less than r, that means x minus a is less than r and greater than negative r. So x is less than a plus r and greater than a minus r. So this is your interval of convergence. Okay, this is your interval of convergence. So what they're doing here when they add in this condition here is, again, they're saying, hey, if you're going to take a function and represent it as a power series, please recognize that the function will only be equal to its power series over an interval of convergence. Okay, so that's very important. Very important indeed. But now what we want to do is we want to determine these coefficients. So let's start off at c sub 0. Okay, well, all right. What would f of a equal? F of a would equal c sub 0 plus c1 times a minus a plus c2 times a minus a squared. Okay, let me draw a little separator here. Okay, continuing, c sub 3 plus c3 times a minus a cubed, and then so forth. So what do all of the terms, what's this term equal here? A minus a. What's that equal? Shout it out to me. That's right, Renaud, 0. Here a minus a is 0. Here a minus a is 0. So that means f of a is equal to c sub 0. Okay, and you determine now what c sub 0 is. We have a formula that will work all the time to determine c sub 0. Okay. Are there any questions on that? All right. Well, so let's see. What's next? What's next is to determine what c sub 1 is. That's the next coefficient. Okay. So one moment here. One moment. All right. So let me go ahead here. I don't think I have any more room at the bottom, so I'm gonna have to rewrite the power series again. But are we okay with the first coefficient equaling the function evaluated at a? Are there any questions on that? Okay. Well, let's continue. Let's go back here. Let me write down my power series for my function, the general form of it. Hold on, got a typo here. Okay, now what I want to do, I mean, I know that, well, let me be a little more clear here. Again, we have our interval of convergence, and I'll note that we already determined that the first coefficient equals f of a. So now let's go after the next coefficient, c1. Well, what I can do is I can take the derivative of my function. And if I do so, what I'm going to get is c1 times 1 minus 0 plus, oh, sorry. No, that's right. Because a is a constant, right? Plus c2 times 2 times x minus a to the first power, okay, plus c3 times 3 times x minus a squared, and so forth, right? Okay, so f prime of x equals c1 plus 2c2 times x minus a plus 3c3 times x minus a squared. Okay, now what we're going to do is evaluate the derivative at x equals a. Okay, I'm going to evaluate the derivative at x equals a, and I'm going to pick that value of a because I want to be able to determine what c1 is. Well, f prime of a would equal c1 plus 2c2 times a minus a plus 3c3 times a minus a squared, and so forth. So therefore, what's c1 equal to? What's c1 equal to, class? Well, f prime of a. That's right, Lapine. That's right. c1 equals f prime of a. Because, again, all of these terms here equal 0, right? All of them. So now we have a formula to determine c1. Okay, so far so good? Tom, question, you're good?
Oh, yeah, no, I was just saying yes.
Okay, excellent, excellent. Thank you, thank you. Okay, well, now let's see here. We know, you know, in our power series, we have identified what c sub 0 is, that coefficient. We've identified, you know, the first coefficient, c1. We know how to get those based on these formulas. If I wanted to find the third coefficient, c2, what do you think I would do with my function? What would I have to do to determine the next coefficient?
Take the second derivative?
That's exactly right, Maria. We'd have to take the second derivative. And let me show you that in the book here. Okay, let me show you that in the book. So if we go down a little bit, okay, here, they take the second derivative. And if you take the second derivative, well, I'll tell you what, let me go to the whiteboard. I mean, this is so important, it's worth doing, even though I gotta rewrite the, you know, rewrite it. I'll do it, it's worth it. I can write it quickly. The power series. And so forth. All right. So f prime of x was equal to c naught, or c sub 0 plus c1 plus 2c2 times x minus a plus 3c3 times x minus a squared. Okay. Okay, now let's take the second derivative. Second derivative is going to equal, okay, it's going to equal something plus something, and then of course the terms continue. But can you tell me what's going to go in the first blank there? And I'm talking non-zero, entries. So I'm taking the derivative of the first derivative here of my function to get the second derivative of my function. What would the second derivative equal? So you're taking the derivative of this here. Okay, Renaud, 2c2 is right in the first spot. What's going to go in the second spot?
6c3.
6c3, that's right, Lepine. Or we could write that as 2 times 3 times c3. Times, sorry, x minus a, right? So if I wanted to figure out what now c2 is, okay, I could put in x equals a in the second derivative. And if I do that, I'm going to get 2c2 plus, 2 times 3 times c3 times a minus a plus, and all the terms are going to go to 0. Everything, all the rest of the terms are going to be 0. So c sub 2 is going to equal f double prime of a over 2. Okay. Are there any questions on that? All right, well, let's summarize here then. Then this is in the recording. Let's summarize what we have. Okay, so the first coefficient in the power series equals the function evaluated at A. The second coefficient in the power series is going to equal the function, or the derivative of the function evaluated at A. Second coefficient is going to equal 1/2 times the second derivative of the function evaluated at A. What do you think the third coefficient is going to equal?
1/3 times the third derivative.
Almost right, Maria. It's actually going to be 1/6 times the third derivative. Because remember, the coefficient in front of the, well, we had that 2 times 3 in front of C3. I'll show you in the book, but the third coefficient is going to turn out to be 1/6 times the third derivative at of the function evaluated at A. If we go to the book, well, let me see here. Let me just ask you, we'll go to the book, but what do you think the fourth, notice here, by the way, notice here, I'll just comment on this. This is equal to the first coefficient, C sub 0, equals f of a divided by 0 factorial. The second coefficient equals, good Nathan, second coefficient equals f prime of a, hold on, I'm going to have more space here. I'm not going to be, I got to have space. I cannot be, you know, got to have space. So let me write this again. Okay, so notice we can write the initial coefficient as f of a over 0 factorial, because 0 factorial is defined to be 1. Okay, that's the first coefficient. The next coefficient, C1, we can write as f prime of a over 1 factorial. I mean, 1 factorial also equals 1. The third coefficient we could write as the second derivative of the function evaluated at a, f double prime of a, over 2 factorial, because 2 factorial is equal to 1 times 2. The fourth coefficient we could write as the third derivative of the function evaluated at a over 3 factorial, because 3 factorial equals 1 times 2 times 3, and that just equals 6. The fourth coefficient, or the fifth coefficient, I should say, is just going to equal, as Nathan pointed out, it'll be the fourth derivative of the function evaluated at a over 4 factorial. So you see, you just keep taking derivatives of that power series, and then substituting x equals a in the result, and then you iteratively solve for your coefficients of your power series. That's what you're doing here. And you can see, I'm not sure, you can see based on like the third derivative, you see how the factorials get involved with those coefficients as you continually take derivatives. You know, and so in general, the coefficient, so like 4, hold on. So for any power series written in this form, in section, you know, that was our idea in 8.7. We said, hey, let's suppose we can write, and maybe I want to kind of have it show, well here. Hold on one moment. Let me take a little of the highlight off. Okay, so we started off in section 8.7 saying that let's suppose our function can be written as a power series of this form, okay? And then we proceeded to try to find values for the coefficients. and of course A would be given to us. That number would be given to us, and then we determine that, well, okay, the coefficients are going to all be computed using this formula. So now, and this makes sense now. This makes sense. It's actually so beautiful, this result. Now, we have then this theorem. We have this theorem that says if your function has a power series representation at x equals a, in other words, if the function can be written as a power series, okay, then the coefficients are given by that formula below. The coefficients, the nth coefficient, I want to be careful. I don't really want to use nth, but the c sub n coefficient in the power series equals the function evaluated, or the nth derivative of the function evaluated at x equals a divided by n factorial. And of course, by the nature of this theorem, we have to assume that our function that we're trying to find a power series for is infinitely differentiable. Okay. And so, you know, we're restricting our attention to those kind of functions. And if we want to write the formula out more generally, here it is here. Okay, so if we write the formula or the power series out more generally, here it is. So mark this moment. This is like, you know, how many remember the time that the moment you got your driver's license, you passed your driver's test and got that driver's license? How many remember that moment? Okay, it's a very happy moment. Jacob and Tal and right, and Baraka, right? That was a happy moment, right? Well, this should be a happy moment too, because you just learned about what a Taylor series is of a function about x equals a. Okay, so we call this a Taylor series of a function f at a, or about a, or centered at a. And now we have the ability to find power series for a variety of functions, okay? A variety of functions that are differentiable. Now, there's a special case if the value of a is equal to 0, okay, then this power series, okay, let me just, hold on, I want to get the blue off. There we go. For the special case where a equals 0, the Taylor series becomes this power series. And it arises frequently. A lot of times we want our Taylor series to be centered about a equals 0, but it won't always be centered about a equals 0. But when it is, we call that a Maclaurin series. We call that kind of function, or that kind of power series, a Maclaurin power series. Okay, so are there any questions on that? Give me a thumbs up if so far you're comfortable with what you're seeing here. Okay, excellent, Jazzy. Well, let's look at an example here. Let's look at an example, and I'm gonna go right to the notes. Right to my notes on this. Okay, so take a moment to copy this example down. And the book has good examples, but I'm going to also be providing my examples so you get some variety. Okay, so take a moment. Okay, so what we want to do here is we want to find the Maclaurin series for, hold on here, find the Maclaurin series for the function f of x equals cosine of 3x over 4 and its interval of convergence. Okay, now for the Maclaurin series, what is a equal to in the Taylor series? What's the value of a? That's right, Nathan, 0. Okay, Michelle, were you going to say that?
Yeah.
All right, all right. We'll give you credit for it too, okay? Okay, so all we need to do is we need to follow the formula. We need to follow the formula. So again, the formula, if we, go back to the ebook. Okay, there's the formula right there. So what we have to do is we have to find enough terms of the series by taking derivatives. We got to find enough terms of the series so that we can detect what the pattern is. And once we have the pattern, then we can actually write a formula for the power series. Okay, so, all right, we got to find f of 0, f prime of 0, f double prime of 0, and f triple prime of 0. We just got to keep doing enough derivatives till we can get the pattern. Okay, so okay, let me go back to the example here. Okay, we'll also find the interval of convergence as well for this problem. So here we go. Here we go. Our function is cosine of 3x over 4. All right, so what I've done is, here's my function, cosine of 3x divided by 4, and I'm going to take the first derivative. First derivative is negative 3 sine of x over 4. Now, what property in calculus did I use to determine the that first derivative? The chain rule. That's right, Renat. All right, so the chain rule, very good. And I keep taking derivatives. So my second derivative will be negative 9 times cosine of 3x over 4. The third derivative will be 27 times the sine of 3x over 4. And finally, the fourth derivative will be 81 cosine of 3x over 4. Okay, and I can keep going, but hopefully these, 5 terms here, these 5, the f of x and the first 4 derivatives, that should hopefully be enough for me to detect a pattern. And I'm going to evaluate all of those at a equals 0, which I do here on the right side. So let me give you a moment to copy down up to here, and then we'll continue talking. Please let me know if you have any questions, okay? Yes, Nathan. All right. Well, all right. So you see, I'm just evaluating then, like f of 0 f of 0 was equal to a fourth. F prime of 0 equals 0. F double prime of 0 equals -9/4. The third derivative of the function at 0 is 0. The fourth derivative of the function evaluated at 0 is 81/4. Okay, so what I can do is I can at least start constructing the series, which I do here. Down here below, I start to construct the series, the power series.
I think I'm just asking, is it typical to write derivatives of a function like you have with the 4 in parentheses, like for the fourth derivative?
Oh yes, when we end up getting to, good question, Nathan. When basically past the first derivative, like like I could write the fourth derivative like this: 1, 2, 3, 4. Right? I could write. I mean, in other words, these mean the same thing. Whether you put the number 4 in parentheses or you put 4 like slashes. But what happens is, it's hard to write like a lot of slashes, for derivatives. If I wanted to do like, the 8th derivative, am I gonna put, 1, 2, 3, 4, 5, 6, 7, 8? That's gonna be a hassle. So that's why we start, using that notation there with the number in parentheses. So that just means fourth derivative. Okay, is that all right?
Yep, that's good. Thank you. Yeah.
Okay, very good. Very good, excellent. Okay, well, so, all right. So I'm constructing the series, and right now I have four, well, how many terms of the series do I have here? I have the first how many terms of the series, of the power series? So of course the power series keeps going, right? That's why I have a plus with the dot, dot, dot. But previous to that, how many terms of the series do I have? Do I know? That's right, Renan. There are 5 terms. And hopefully with the 5 terms of the series, we'll be able to detect a pattern. Let me just see here, one moment. If you look here, if you look at these derivatives, okay? So like I want to say this the right way. The first term of the series has a 1 in the numerator, okay? The second term of the series, it's a -9/4, but there's a 9 there, right? The fourth term of the series, there's an 81 there in the numerator. Now this power series, it's going to go plus, negative, plus, negative. It's clear it's going to be an alternating power series. But could you venture based on the pattern here? Okay, what would the fifth derivative evaluated at 0 equal? in this power series. And you notice I haven't computed the fifth derivative. I'm just asking, based on the pattern that you're seeing here, what do you think the fifth derivative is going to be? All right, Jacob says 0. That's right. So Jacob's noticing that odd derivatives equal 0. Even derivatives are not equal to 0. All right, well, let's take a look at the sixth derivative evaluated at 0. Okay, fifth derivative evaluated at 0. So what's definitely going to be in the denominator?
4.
4. That's right. 4 is going to be in the denominator. And, you know, let me see here, one moment. What do you think is going to be
Negative 729.
Okay. Okay. Good, Maria. Negative 729. That's exactly right. That's exactly right. Put the equals there. So you see the one can be thought of as, we notice that 1, 9, 81, okay, in these non-zero terms. There's a 9 that's in common. Well, 1 can be thought of as 9 to the 0th power. 9 is like 9 to the first power. 81 is 9 to the second power. 729 is 9 to the third power. You see? So when you get enough non-zero terms in the series, you can start to detect like what the pattern is. Okay, are there any questions on that before I go to the next page? Please let me know. It's like a little puzzle that you have to figure out. All right, well then let's go to the next page. The reason, Nathan, it's negative is because the first term here of the series was a positive. The second term, the third term of the series involves a negative. I should say the first coefficient of the series is positive. The third coefficient is negative, and the fifth coefficient is again positive. A positive of fourth, negative 9 fourths, 81 fourths. The sixth term of the series is going to then go negative. Okay. Now, hey, I could go out, I could compute my sixth derivative of my function and actually show that the sixth derivative of the function evaluated at 0 is equal to negative 729 over 4. I could show that. But, there's always a pattern, and sometimes, you can get the pattern based on the first 4 or 5 terms. Okay, so let us continue here. Now I'm going to rewrite the power series on the next page, and I have in there the negative 729 over 4. Okay, so that's the seventh term of the series, right? Seventh term of the series. But remember, you got to be a little. All of these terms are over the appropriate factorials. Okay, so let's again remember what the Maclaurin series, what the formula is, right? For the Maclaurin series. The formula is that the function is equal to f of 0 plus f prime of 0 times x over 1 factorial plus f double prime of 0 times x squared over 2 factorial And then we just keep going. And so when we do that, we're going to get this here. And what I do is I rewrite the power series in a little bit nicer form. Which certainly we can do. And based on that, then I know what the pattern is. I know what my power series is. So a lot of times in the WebAssign, what they'll do is they'll have a multiple choice where they give you, they say, hey, find the power series, find the Maclaurin series for this function, and they'll sometimes you'll have to actually type in the formula, but many times they will give you like 5 choices, and you have to pick the right choice of the 5. Okay, and so it helps tremendously to have written down the first 4 or 5 non-zero terms of the series, of the power series, so that you can establish, hey, what would the right pattern be? And it turns out that this here is the pattern. This is the power series. The -1 to the nth power handles the oscillation. That handles the oscillation. So we go positive, negative, and so forth. The powers in the power series, you notice, are all even powers. X squared, x to the 4th, x to the 6th, and the 1/4 is like 1/4 times x to the 0. So x to the 2nth power handles that. The denominator, there's always a 4 in the denominator of the terms, so the 4 makes sense. And then the factorials, you notice, and again, they don't put it in, but here, you could insert a 0 factorial here under the x to the 0th power. And all the factorials, 0 factorial, 2 factorial, 4 factorial, 6 factorial, okay, all of these factorials here are even factorials. So hence the quantity 2n factorial. And then the 1 and the 9 and the 81 and the 729. Well, you could think of that as 9 to the nth power. Okay, you could think of those terms all at like 9 to the nth power would generate those values. But the choice in WebAssign might not have 9 to the nth. It might have 3 to the 2nth. Well, in fact, 9 to the nth power is just 3 squared to the nth power, which is just equal to 3 to the 2nth power. Okay, and so we can write 9th power as 3 to the 2nth power. And so that handles this. You wouldn't have even imagined at the beginning of Calculus 2 of doing math like this. But now that you're having Calculus 2 and you're learning so many things, you've matured enough to be able to do this kind of math. You've matured mathematically. Renaud says, let's see, hold on. Renaud asks, hold on here. is the x to the 2nth power after each term because of the original formula. The x to the 2nth power is the x to the 2nth power here is part of the formula because all of the powers in the terms of the series, you know, the non-zero terms, they're all even powers. X to the 0 power, x squared, x to the 4th, x to the 6th. I don't want to have an odd power there. So if I take x and raise it to the 2nth power, that will ensure for as the index n goes from 0 to infinity, every term, every non-zero term in the power series is going to have an even power. So like x to the 0, for instance, is like x to the, hold on here. Yeah, x to the 0 power is like x to the 2 times 0 power. X squared is like x to the power 2 times 1. X to the 4th is like x to the power 2 times 2. X to the 6th is like x to the power 2 times 3. Hence, x to the 2nth power. Renaud, does that make sense? Does that help you? Okay, you're welcome. Nathan, why did we start at n equals 0? Well, it's okay to do that. You can start a power series at n equals 0. Now, if I were to change the index from, it's easier. It's easier to write out the formula if we start the index at n equals 0. If we were to start the index at n equals 1, it would make the power series a little more difficult to write out. Actually, let me go to the whiteboard. Let's talk about that real quick. It's a good question. So the series, the power series for this example, you know, we're getting a lot of good questions. They're going to help you with other problems too. So the power series is this. But sure, we can write that power series starting at n equals 1. We could write that if we wanted. We could change the index. And if we change the index, then what would we do? Like we wouldn't have -1 to the nth power. We'd have -1 to what power? Maybe what I'll do is write it below. I think it'll be a little easier. That's right, Nathan. Yeah, we'd have -1 to the n-1 power. We'd have 3 to the what power? What would the power be on the 3? That's right. Good, Nathan. 2n-2. Because 2n-2 is 2 times, that's 2 times n-1. And then x to the 2nth power would have also be x to the 2n-2. And then 2n factorial would be, hold on, now let me just give you one moment. I got to be a little bit careful here. Yeah, that would be also 2n-2 factorial. So this is a perfectly acceptable way to write out the power series for this function cosine of 3x over 4. But which power series is nicer? Power series 1 or power series 2? Which is a nicer power series? A little bit nicer looking. I agree, Jacob. Power series 1. And that's why they start the index at n equals 0. Okay, are there any questions on that? Okay, you're welcome. They always try to pick an index where it makes the power series look nice, the nicest possible. Okay, well, that being said, now we have a little more to do on this problem. So we've found our power series, or Maclaurin series, for the cosine of 3x over 4. Now, but for what x values is this true? What's the interval of convergence? To answer this, we have to find the interval of convergence using the ratio test. Okay. So it works just like in section 8.5. You were given power series there. You didn't know where those power series came from in section 8.5, but you found intervals of convergence for those power series. Well, we're going to do the same thing here. So we'll use the ratio test. Let me know, are we ready to move to the next page? Give me a thumbs up when you're ready. All right, Maria's good, and Leping and Abadara. Jacob and Tal, excellent. Okay, here we go. We're going to use the ratio test to find the interval of convergence. So, well, and I'll just mention, so here is the nth term, right, of the series. So a sub n is equal to -1 to the nth power times 3 to the 2nth power times x to the 2nth power divided by 4 times 2n factorial. And now we're going to apply the ratio test. So the ratio test says, all right, look at the absolute value of the ratio of the n plus first term to the nth term. We have a fraction divided by a fraction here. So I'm going to take the top fraction and multiply it by its reciprocal, which I do here. And then we group the like terms. Okay. Let me give you a moment to catch up here. Let me know if you have any questions. Okay, so the factorials, if you take 2n plus 2 factorial, that's just going to be, 2n plus 2 times 2n plus 1 times 2n factorial. Okay, and the reason that's good to write it that way is because then you get simplification. You get simplification here. Okay, so it's no different than like if you were to take, 5 factorial. 5 factorial is 5 times 3. Sorry, let me do this again. 5 factorial is equal to 5 times 4 times 3 times 2 times 1, right? 5 factorial. Or 1 times 2 times 3 times 4 times 5. But we can write 5 factorial then as 5 times 4 times then 3 factorial, you see? So we're doing the same trick here so that the 2n factorials simplify out. And so now the ratio is equal to what you see here, the absolute value of -1 times 3 squared times 1 over 2n plus 2 times 2n plus 1, right? Times the x squared. When you take the absolute value, the -1 goes away. And why does the x squared here have no absolute value around it? Normally, like the term with the x on it, you keep the absolute value around it. But here, I'm dropping the absolute value on that term. Why would that be?
Any number squared is always positive.
That's right, Maria. Excellent. So this ratio, the absolute value of the ratio of the nth term to the n plus first term to the nth term, will approach 0 for all x, because even if x is like very, very big, you square x, you're letting n go to infinity. So the denominator eventually, the 2n plus 2 times 2n plus 1, that's gonna get larger than the numerator, and in the limit, it's gonna approach 0. So, and 0 is always less than 1. So for all x values, the absolute value of the ratio approaches 0, which is less than 1. And what's that tell you about the interval of convergence? What would the interval of convergence have to be then for this problem? That's right, Renat. It'd have to be from -infinity to infinity. And I have that written on the next page, which I'll show you. But give me a thumbs up when you're good with this page, and then I'll go to the next page. And please let me know if you have any questions. All right, so when you're ready, we'll move on. Okay, Nathan's good, Renat's good, Michelle's good. Tall's good, okay. So, maybe I'll wait for one more person to give a thumbs up. Okay, Maria. All right, Leping. All right, so then, all right, Marcus, excellent, excellent. So here we go then, here we go. Here's our interval of convergence. It's from negative infinity to infinity, and the radius of convergence equals infinity. Okay, so are there, let me just see here if there's maybe, yeah. I want to go to an example in the book here. Let me go to, hold on everybody. Yeah, I want to go to example 4. Now here, in example 4, they want you to find a Maclaurin series for the sine of x and prove that it equals the sine of x for all x. That basically means what they're saying there, one moment. Sorry. What they're saying when they say this, okay, sorry, I gotta get the list. I'm telling you, it's picky. Hold on, we're gonna get it right. I'm gonna highlight this whole thing. Okay, so find the Maclaurin series. So this is example 4 from section 8.7. Find the Maclaurin series for the sine of x and prove that it represents the sine of x for all x. So what they do is they do what we did with the previous problem. They take some derivatives, and they go out to the fourth derivative of x, and then they evaluate these derivatives at 0. And based on that, I mean, based on what you see here, they comment that the derivatives repeat in a cycle of 4. The reason they say that is, if you notice, the first derivative is 1, the third derivative is -1. Okay, what derivative is going to equal 1 again? So like the first derivative at 0 equals 1. The third derivative at 0 equals -1. What would the, well, let me say it another way. Do you see there how f of it, so like in the solution, f of x equals the sine of x. But after you take 4 derivatives, you're back to the sine of x again. You see that? F of x equals the sine of x, and then the fourth derivative of x equals the sine of x. So you end up getting derivatives that repeat in a cycle of 4. So like the first derivative of x is the cosine of x, that means the fifth derivative of x would be the cosine of x. So you basically, with this knowledge, you have an idea of the pattern of the coefficients. It's going to go 1, -1, 1, -1, 1, -1. And it's going to be on what powers? Would it be on even powers or odd powers? That's right, Renaud, odd derivatives. And odd derivatives go with the odd powers. So if we go down a little bit here, okay, try to highlight this here too. The Maclaurin series is going to equal x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so forth. And then there is the pattern. The pattern gives us the power series, the summation n equals 0 to infinity of -1 to the nth power. The -1 to the nth power handles the oscillation. And then, but now you have x to the 2n plus first power, okay, because you have odd powers over 2n plus 1 factorial, because the factorials are odd. Okay? And it turns out that if you, well, are there any questions on that? Any questions on how they get the power series? All right, give me a thumbs up if you're okay with this. And we'll move on. Okay, Renaud's good, Leping's good. Tall's good. All right. Well, it turns out that if they use the ratio test on this, it turns out that this power series will equal the sine of x for all values of x. Okay, so essentially the sine of x is equivalent to its power series. Okay, and they use the ratio test to show that. But what I want to show you here, I want to go down a little bit. Actually, hold on, let me go to the whiteboard. Let me go to the whiteboard and write this. So the sine of x is equal hold on here. One moment, class. The sine of x, yes, equals this power series. And that's true when x, for all values of x. In other words, the interval of convergence is infinity. Okay, one moment. But I find the radius of convergence really to be less informative than I mean, once you have the interval of convergence, that to me is the most important thing. Okay, now what I want to do is I want to write what are called Taylor, or in this case, Maclaurin polynomials, but I'll just call them Taylor polynomials. Okay, so the let me just see here. Hold on. I'm going to have to write down a little bit more. One moment. How's that for erasing, huh? Hey, I think I learned how to do this. I got to do it horizontal. I was doing it up and down, but I got to go horizontal. That works. Learn something new every day, right? So the terms are going to equal x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so forth. And there are polynomials called Taylor polynomials, or in this case it would be Maclaurin polynomials, because a is equal to 0 here, right? A is equal to 0. So you see, T1 of x would be equal to x. That stands for Taylor polynomial of degree 1. Okay. T sub 3 of x would be x minus x cubed over 3 factorial, which is x minus x cubed over 6. That's the Taylor polynomial of the 3rd degree. So what you're doing is like there, I took the first 2 terms of the power series. And I don't have to worry, I mean, I'll just, and then, I can do the 5th Taylor polynomial, which would be the first, then 3 terms of the power series, because it's up to degree 5. It's up to degree 5. So that would be x minus x cubed over 6 plus x to the 5th over 120. Okay. Now, are there any questions on this? This is a concept that's going to come up in section 8.8. 8.8 we'll cover on Thursday. But these are what are called Taylor polynomials. Right? And they are generated from the power series. So what's really cool is to graph the Taylor polynomials along with the sign of x on the same graph. And they do that in figure 2 in section 8.7. So if I go to section 8.7, okay, if I go there, and this relates to example 4, okay, all right, here, what they've done in figure 2 hold on. So there are the three Taylor polynomials, T1, T3, T5, and they've graphed the polynomials along with the sign of x. Now all the polynomials agree perfectly with the sign of x at a equals 0 or x equals 0. Of the three polynomials, T1, T3, and T5, which polynomial, as you move away from x equals 0, as you move away from there along the x-axis, which Taylor or Maclaurin polynomial does the best job in approximating the sign of x? T1, T3, or T5?
I have a curiosity question though. Based on what you wrote on the whiteboard and what this says here, the denominator for both x to the third and x to the fifth are 3 factorial. But what you wrote down was that T5 has a denominator of 5 factorial for x to the fifth.
You know what? They have a typo here. Thank you, Maria. Wow, good catch.
Okay.
So Maria's noting that for T5, they have a 3 factorial under x to the fifth power. That's incorrect. It should be 5 factorial. All right, good catch. You know, the book has probably, who knows, 100 million words and 100 million, well, maybe not 100 million, but let's say 10 million letters and numbers. Probably more, though, probably maybe 50 million. Hey, you know, occasionally, but I'm glad you spotted that, Maria. Thank you. All right, so which polynomial does the best job in approximating the sign of x? T1, T3, or T5? What do you think? And I'll look for a few responses here. Okay, Renaud and Jacob agree. Maria agrees. Okay, it's the 5th degree Taylor polynomial, T sub 5. And they mention here, notice that as n increases, the Taylor polynomial becomes a better approximation to the sign of x. Now, why would T sub 5 be better, a better approximation to the sign of x? Why would the 5th degree polynomial be a better approximation to the sign of x? Just intuitively, why should it be? That's right, Renaud. It's more terms of the power series. The sign of x is equivalent to its power series. So if you create polynomials and take more terms of the power series to create your polynomial, that polynomial should approximate the sign of x over a larger window of x values. Now, of course, the T sub 5 fails, right? Eventually, even T sub 5 fails. So if you want to approximate the sign of x with over a wider range of x values, you have to take more terms. And there's something else really cool here. Are there any questions on that before I move on? We'll take our break in just a few minutes, but I just want to show you a few more things. Okay, I'll show you one more thing here in the book. So in example 7, they want you to represent the sign of x as the sum of its Taylor series centered at pi over 3. So in this problem, you are going to take derivatives of the sine and then evaluate the sine wave or those derivatives at pi over 3. Okay, so this is now a true Taylor polynomial. In the sense, it's not a Maclaurin. I'm sorry, it's a Taylor series. It's not a Maclaurin series because a is not equal to 0. Here, a equals pi over 3. But the idea is the same. The idea is the same. Generate enough terms, evaluate enough coefficients, substitute those coefficients in the Taylor series so you can detect a pattern. You see, that's the idea. So they do that. And in this case, based off of the, hold on here. I want to just, I think I want to have a little more, I'll highlight this. All right, so do you see what they're doing there? How they're just substituting in the coefficients into the Taylor polynomial formula. So again, let me just go, the Taylor polynomial formula, I'm sorry, the Taylor series formula. Hold on here. Is right here. This is the Taylor series formula. And A equals pi over 3. So you establish what you determine what your coefficients are. You plug them in the formula. And then based off of that, with enough terms, you ought to be able to determine what the formula is for what the general formula is for the power series. And so now back to this example. Here we go. Back to, we're looking again at example. We're looking at example 4 here. So I'm sorry. I'm on the wrong. We're looking at not example 4. We're looking at example 7. Let me find. There we go. Example 7. So, here we are. Taylor series for the sine of x about a equals pi over 3. There are all the terms. And it turns out that then they can write the Taylor series as what you see below. As what you see in the box, in the blown ups there. So what they do is they actually write this series as the sum of two separate series. They write, I'm sorry, the sine of x can be written, in other words, to write out the general formula for the Taylor series for the sine of x about pi over 3, you need to have two power series added together. One power series for the even terms, another power series for the odd terms. Okay, so it's kind of an interesting problem. It's kind of an interesting problem for sure. For your particular problems in your homework, I think, well, normally you'll be able to get the representation of the function with just one power series, but this one you needed to have the sum of 2 power series. Okay, are there any questions on that? Okay, I'm going to stop the recording then. And we'll continue on. I want to do another lecture from section 8.7, but I'll stop the recording for this part.